All right, so let's start. Welcome everyone to the Schubert seminar. So before we start, I'll mention that we're gonna have three talks in consecutive weeks. So we're starting this week with Nate Lesnevich from Oklahoma State. We're gonna have Kamil Riklevich next week, and then Mingji Yang 2 weeks from today. So please join us every week. And then we're gonna have a little Thanksgiving break. But today, as I said, we're happy to have Nate Lesnevich from Oklahoma State telling us about combinatorics for GKM theory and the dot auction. So please take it away, Nate.
Awesome. Yes. Thank you for having me. And we should, yeah, really happy to be here. Let's go right in with a little bit of background, a little introduction. So, right, our setup, we're going to let T be a complex torus, C star to the end, and X a variety, complex variety, such that T acts on our variety. And overall, right, we're interested in computing the T equivariant and ordinary cohomology using this combinatorial framework called GKM theory. GKM for Goreski, Kottwitz, and McPherson. This setup is possible when the fixed point set of our torus action is finite. There are finitely many one-dimensional torus orbits, and our variety satisfies this kind of technical condition called being equivariantly formal. Now, for our purposes, right, especially in how I've set it up here, it is good enough to say that X doesn't have any odd cohomology, which in a lot of cases we're going to end up sort of getting out for free things that are already known to not have any odd co have only even cohomology. So this includes, right, projective space, Schubert varieties, Combinatorial varieties, regular semi-simple Hessenberg varieties, flag varieties, ton of different stuff, right? Many, many more. Uh, the key combinatorial construction behind GKM theory is the GKM or moment graph, right? So we have these finitely many torus fixed points. Those are going to form the vertices of our graph, right? Part of being equivariantly formal means that our one-dimensional torus orbits, right, one complex dimensional torus orbits, are going to connect two different fixed points, right? So those are going to be the edges in our GKM or moment graph. And finally, we need a little bit of extra information, an edge labeling that we're going to get from torus weights. So the way I think about this, at least, right, if I have like the simplest setup possible, I have my like one torus C star acting on P1 or the Riemann sphere or whatever you want to call it, right? Just by multiplication, I have two T fixed points, right? Zero, nothing's going to happen with multiplication there. Same with our point at infinity, nothing's going to happen with multiplication there. And we have one complex dimension sort of connecting the two. So that's going to translate into a graph with a vertex for zero, a vertex for infinity, an edge between them, and in this case, a torus weight label of just t. Now, what does this look like for, Pn in general, P2 specifically? If we have Cn plus 1, or Cn acting on Pn minus 1 by coordinate-wise multiplication. So I have here T1 through 3 being the torus acting on P2 by this multiplication here. We have three fixed points, right? It's projective, so we can scale however we want, and multiplication isn't going to do anything to any of our coordinate points. Right, so we have these three torus fixed points. Those translate to our three vertices in this graph, right? Edges between them being one-dimensional torus orbits, they end up connecting all of them in this case, right? And for the labels, the way that I would think about it is like, how are we getting from our first coordinate vector to our second coordinate vector? That's sort of moving along T1 and T2. So I'm going to label that T1 minus T2. How do we get from the first to the third, that's sort of multiplication along T1 and T3. So I'll label that T1 minus T3. And overall, if we have this action generalized, right, what we're going to get out of it is the complete graph, right, all of the possible connections that we see, and the label on edge from I to j is always going to be Ti minus Tj. So once we have this set up combinatorially, right, we can forget kind of that this came from a geometric object at all and really work with the graph. That's where a lot, at least from my perspective, and uh, a large part of the value for this aspect of GKM theory. So, what does this actually tell us about cohomology? The GKM theorem, right? Uh, we need a definition to start, right? A spline on a graph with this edge labeling. It is an assignment of polynomials to vertices such that along every edge, right, we'll have two polynomials on either side. The difference along that edge needs to be divisible by whatever label we see there. Uh, or equivalently, it needs to be in the ideal generated by it. That's how I have it written over here. And if we collect all of the possible splines on our labeled graph together into this set, I have MG, right? That set is going to form a graded module over the polynomial ring in like the most natural way possible. You multiply polynomials everywhere you see, as well as a graded ring by pointwise addition and pointwise multiplication. And the grading is also what I would think is the natural grading on this. If you see polynomials of homogeneous degree k, that's living in the degree k piece of this. And the GKM theorem is that when you have this GKM graph coming from your T action on the variety, this sort of algebraic combinatorial object is isomorphic to T equivariant cohomology. And not only that, part of one of the other things that you get out of this equivariantly formal situation is a quotient map down to ordinary cohomology. So one of the big helpful things with this theory is once we have our combinatorial setup for this graph, we can do a lot of equivariant and ordinary cohomology calculations, really just playing around with graphs and polynomials. So what does this look like for the first example that I showed, right? Like the simplest thing that we could see, right? For P1 with the action I showed before, it looks like pairs of polynomials such that their difference is divisible by T, right? So I have this F and G, a couple of examples of this playing out, right? We can sort of always put constant thing everywhere because all of the differences are zero. Or we can try and be a little bit selective about the support of our spline, right? Placing zero somewhere and having non-zero polynomials elsewhere, and all sorts of different combinations here. You can, I mean, these are easy to check. It's kind of a local condition. You just take the difference and see whether or not it's a multiple, right? In this setup, right, we have this 1, 1 and 0t. They actually form a minimal homogeneous module generating set of that module slash ring of splines, right? So they project down to a vector space basis in this quotient, giving us essentially a vector space basis for ordinary cohomology in this case, right? What does this look like for the other one that I showed you, right? If I have C3 acting on P2 the way we saw before, well, we can always put the constant spline, right? Ones everywhere. That's going to work. I have this homogeneous degree 1 spline over on the left and this homogeneous degree 2 spline over on the right. And it turns out, and here in this case, you can make some like relatively straightforward arguments, saying, with these three, I can build any spline that I want, right? These are minimal homogeneous generating set for splines on this graph. And general PN works out essentially the exact same way. Now, I mean, this is a Schubert seminar, right? So we talk a little bit about flag varieties. And really what I want to pull away from this sort of introduction period piece is that once you have your GKM graph, you can go off to the races. You can compute equivariant and ordinary cohomology. What does that look like for flag varieties and like a bunch of subvarieties of flag varieties? Well, the vertices of our graph, our T fixed points, are going to be Weyl group elements, right? One-to-one correspondence. Our edges, our one-dimensional torus orbits, are going to be built from right multiplication by a reflection or a transposition, whatever word you want to use for that. And how are we going to label our edges? Evaluating by the corresponding root. That's going to give you some vector. Turn that vector into a linear polynomial, right? So the big takeaway, right? If I tell you which Weyl group elements to use, which reflections to use to build your edges, right? The labeling system is always going to be the same as long as you don't have some crazy T action, right? We can construct the GKM graph and thereby compute equivariant and ordinary cohomology for pretty much every GKM subvariety of the flag variety, as long as it lines up with the same torus action. Cool. So what does this look like for some familiar objects, right? So if I want to build this up for the full flag variety, I'm going to need every single element of my Weyl group, and I'm going to want to be able to right multiply by every single transposition. Right? That'll build out my graph for the full flag variety. If I want to do this for a Schubert variety, I can take all of the T fixed points that are contained in my Schubert variety, right? So V for all V less than or equal to W, and I'm still able to connect them with any right multiplication by a transposition that I want to use. Opposite Schubert varieties, exact same way, right? Just on the other side, you take all V greater than or equal to W, and you're still connecting with every edge that you can. If I want to build out the permutahedral variety, right, I still have every T fixed point, but I'm not allowed to build every single edge that I like possibly could combinatorially. I'm only allowed to build edges with a right multiplication by simple transpositions. And maybe, you know, more generally, at least than flag and permutahedral, if I have a regular semi-simple Hessenberg variety, that's going to contain every single T fixed point, right? So I need every element of my Weyl group, and I'm going to be selective about which transpositions I'm allowed to use based off of how I build my Hessenberg variety. Now, I'm not going to define what a Hessenberg variety is, and I'm not going to say very much about their geometry, in large part because the one of the like values that I've found in here is not needing to do that in order to work with GKM theory, right? As long as I have the combinatorics of which transpositions I'm using down, I can build my graph and I can do computations without involving very much like geometric information, right? So we're going to focus for the rest of the talk on Hessenberg, regular semi-simple Hessenberg varieties in types A, B, and C. So our Weyl groups are going to be permutations and signed permutations, or the hyperoctahedral group for signed permutations if you like that name for it a little bit better. So I need to tell you how to label the graph, right? For the symmetric group, if I have right multiplication by a transposition, ij, the evaluation is going to give me T sub W of I minus T sub W of J. So I have here just sort of zoomed in on one possible edge in a GKM graph, corresponding to right multiplication by 1, 2, because it switches those first two positions, and labeling T1 minus T3, because those are the numbers that it's changing around. Now, what does this look like for the full flag variety case, right? Where I use every single transposition. I'm allowed to swap all ij, right? Well, for S3, it's going to give you this graph with this labeling system. You can see, I mean, you can pick any edge that you want. This one is right multiplication by 1, 3. It also switches the numbers 1, 3. It's labeled by T1 minus T3, and I can start building splines. So this is a perfectly good, homogeneous degree 1 spline on this particular GKM graph. I can make more degree 2 ones. I can sort of do this all day, right? What does this look like for the Bermuda-Hedral variety? Well, I'm only allowed to use simple transpositions. So I'm only allowed to switch 1 and 2 and switch 2 and 3. Right, so I just have fewer edges in my graph, same labeling system as before, and I can still build splines. Now, one of the things that you get out of this, sort of at a base level, is the fewer edges I have, the more splines I can make. I have fewer divisibility conditions I have to worry about. So if I were to add these back in, I no longer satisfy a divisibility condition. The spline that I have written down for the Bermuda-Hedral isn't a valid one for the full flag. All right, so that's sort of what it looks like for the standard permutations. For signed permutations, I'm going to use bar notation so that I bar is negative I. Signed permutation, or the type BC Weil group, are permutations of 1 through n and negative 1 through n that satisfy this symmetry with negative numbers. I need W of negative I to be negative W of I. I'll write one line notation with brackets just to make sure we don't have any confusion with normal permutations. So W2 contains these 8 elements, right? And the sign transpositions, what are we allowed to use to build our graph? Well, it's still switching I and J, just with the knowledge that if I switch I and J, I also need to switch negative I and negative J. And the same for any sort of mixture therein, and a little bit of extra, I'm allowed to switch I and negative I as well, right? So again, if we do this for, I mean, as small as of an example as we can really get at, right? Signed permutations on 1 and 2, these are the same 8 elements we saw before. Right multiplication, allowing myself to switch the numbers that I see in one line notation and negate the second, and I'm going to label by which of those numbers got changed, right? So if I'm just negating something, right, moving from 1 to negative 1, all right, T1, if I'm switching numbers of different sign, I'll have a plus. And if I'm switching something like 1 and 2, sort of in the same way that it worked for the normal symmetric group permutations on n, it'll be, in this case right here, T1 minus T2, because it's switching 1 and 2. All right. And we can build splines the same way that we did before, checking divisibility conditions edge by edge and building out our polynomials. Now, there's one last sort of like algebraic structure I want to put on this set called the dot action. So in the general case, even if it's not type, and it could be type D or really any reflection group, you can build this out. We have a dot action of W, our Weil group, on the set of splines built in this manner, right? So this dot action works by moving polynomials around by left multiplication. That's what this little W inverse inside of here is going to end up doing. and acting on our polynomials, really the indices of our polynomials, by the Weyl group element, right? So what does this look like for the transposition 1, 2, switching 1 and 2, acting on this spline that we saw a couple of slides ago, right? Well, I'm moving these polynomials around and I'm acting on the indices that I see. So this 2, 1, 3, if I left multiply by 1, 2, it's going to send me to the identity. And I'm switching 1 and 2 because that's what 1, 2 does, right? Same up here. This moves this 2, 3, 1 into this 1, 3, 2 because it's switching the numbers 1 and 2. And I see this T2 get turned into a T1. And with any set of transpositions that you take, even if it maybe doesn't correspond to a geometric sort of Hessenberg variety situation, this is going to preserve all of the spline conditions, right? A well-defined action on this set. Now, oh, yeah, this is just a different example. You can act by another element. If I decide to switch 2 and 3, I'm going to move my polynomials to different places, and now I'm going to switch 2 and 3, right, in the indices that I see. So, right, all of this structure interacting with each together, right? So we have a graded module structure. If I take the irrelevant ideal, right, the ideal generated by all of the variables, right, in my polynomial ring, that quotient is going to be a graded vector space. This is the same thing we saw before that I mentioned with, T equivariant cohomology going down to ordinary cohomology. That's what this math is, right? We get out a graded vector space. This ideal, well, this quotient, right, is W equivariant, right? Acting by W is not going to take you out of this set. So the dot action on my set of splines induces a dot action representation on this graded vector space. Now I have a Weyl group acting on a vector space that is, I mean, definitionally a representation of that Weyl group. And so we get a graded character, uh, all built sort of from this data of what Weyl group am I working with, what transpositions am I allowed to use. So for an overview of the structure, right, I'm starting out with a set of transpositions. Probably that's coming from some sort of Hessenberg variety, but maybe I just have some sort of pleasant combinatorial way of deciding what I'm allowed to multiply on the right by. I build my GKM graph that gives me my set of splines with like the natural ring structure on it. That set is a module over the polynomial ring, and this quotient gives me a graded vector space. Also associated to it is this W action, the dot action, so it has a W module structure, and all of this combines together to give you a graded character. And this graded character is like the goal object in a lot of the research that I end up doing. I want to be able to compute this character down here, and I really want to be able to do it just from looking all the way at the top, right? I want to be able to take in a set of transpositions, do some combinatorics, and tell you exactly what this graded character is. Now, I've been using the letter L uh, for left because I'm not going to really go into it too much. I'll keep this talk for the sort of the second portion of it entirely on this side. But you can give your set of splines a slightly different uh, module structure. So multiplication isn't going to look like multiplication at every single point with the exact same polynomial. It gives you a surprisingly different graded vector space structure and a different character. So If I say the left character, it's because there's also a right character that I'm not going to talk too much about. But a lot of the computations that I'm going to show you a little bit later today, right? They're all going to be in the language of this left character here. With a little bit of variation, you can compute this right character as well. All right, so I think now might be a good time for like a 5 minute break because the next section is getting more results specific. And this is sort of the end of the overview of how this is all structured.
All right, sounds great. So let's take a 5 minute break then.